when people put a liquid into a container and leave it, often what they'll notice is that part of it has evaporated when they come back. And this is because at the surface of the liquid, some of those molecules will have enough energy to escape into the gas phase. After enough of them have escaped into the gas phase, though, some of them will run back into the liquid, and the molecules on the surface of the liquid will be able to recapture them if the energy is low enough, or if it runs into it hard enough. At some point, the amount of molecules leaving the liquid is going to be equal to the amount of molecules running back into this liquid. At that point, it will reach an equilibrium, and the amount of pressure that this gas is exerting is the vapor pressure when it is at this equilibrium, where the same amount of molecules leaving is equal to the amount coming back. The pressure at that point is the vapor pressure. And the vapor pressure is different for all the molecules. What the vapor pressure is going to depend on two things. It's going to depend on the intermolecular forces between the molecules and the temperature. Here are some examples of different vapor pressures for different molecules. Here is a column of mercury at standard atmospheric pressure. When I inject some water into it and it floats to the surface because it's less dense, I'm going to notice that the column of mercury is going to decrease. And it's funny because people would think that since I've injected more stuff into it, the water would raise the reading on the mercury, but it's in fact not the case. Because some of this water is going to become a gas, the gas is going to compete with the atmospheric pressure. The pressure of the atmosphere is pushing down here. But the vapor pressure, the molecules of the water are going to be pushing back down this way. So what I can do is calculate the vapor pressure of something that's in here by subtracting the new reading of the mercury from what it would be at atmospheric pressure. So I subtract 736 from 760 and I get 24. So the vapor pressure of water is 24 millimeters of mercury. So next is ethanol, this regular drinking alcohol. It has a vapor pressure of 65 millimeters of mercury. And then lastly I have diethyl ether, and I think that's what Johnny Depp puts in his eye in that one movie, Fear and Loathing in Las Vegas. But anyways, it has a very, very high vapor pressure compared to the other two, so you shouldn't leave that open to air, otherwise it'll all be gone. It'll be in the gas phase. That's 545 millimeters of mercury is the vapor pressure, because it would only rise 215. This is how much this gas would be pushing down on it. So what I wanted to say about this is that I notice a large disparity between the vapor pressures. And what that is caused by is the intermolecular forces. If I look at these from left to right, I'm going to notice that they decrease from left to right. The intermolecular forces between water are much stronger than diethyl ether. Water has very polar bonds. Diethyl ether does not. And if I think about it logically, it makes sense. Something that has strong intermolecular forces, it's going to be harder for one of those molecules to leave and become a gas because their forces of attraction are much stronger. Something like diethyl ether, where the intermolecular forces are relatively weak, it's easy for it to become a gas because they don't hold on to each other that tightly. And temperature, the other determining factor of vapor pressures, should make a lot of sense, because if I heat something, the molecules are going to have more energy, so more of them will become a gas. And one more thing is a formula for determining the vapor pressure given a temperature. So as I said, the temperature will cause the vapor pressure to change. The vapor pressure might be 24 millimeters of mercury at standard temperature and pressure at 760 or 1 atmosphere and 25 degrees Celsius, whatever standard pressure is, I forgot. It will change if I heat it. So this is an equation that will give me what the new vapor pressure is. This natural log of the vapor pressure, this is what I would be looking for, is equal to negative delta H vap. Delta H vap is the heat of vaporization. It's the amount of energy it takes to vaporize 1 mole of whatever it is I'm looking for. R, everyone's familiar with, and then T is the temperature, and plus C is just the differential equation constant.